We have allotted about 1 minute per slide. Hopefully that was clear, and you don't have a 5-minute script set up. So I will not be incredibly harsh about the timing, but after about a minute, I'll let you know it's been a minute. And then after about 10 or 15 seconds, we'll just advance the slides on and go to the next person. So yeah, try to listen for my 1 minute prompt there if you aren't done before. And I think unless there are any further questions or concerns, we can go ahead and get started going through the list, which is largely alphabetical. And starting up will be Katherine Benedict. So when we see her slide here, we can get started.
Yeah, so I'll get started. One thing that we've been interested in is better understanding how smoke that gets lofted rapidly up into pyrocumulus, how aerosol and the coatings and how condensation of organics occur, and those type of plumes compared to those that are in the boundary layer, and what we can learn by using some aircraft observations. So we took some of the FireXAQ observations from pyrocumulus convection during one of their flights. And we're actually comparing that to a lot of their flights where they just have fresh boundary layer smoke. And if we look in the middle where we see the gas phase data, we calculated the fraction expected based on partitioning theory using the gas phase concentrations from the whole air canister samples. And we see that only one nonene had any significant partitioning to the aerosol phase. That's the furthest left. Everything else is on a different scale and is a significantly less than 1%. We are calculating is in the aerosol phase. And this is really
1 minute.
Based on the volatility of those compounds. We looked at the profile vertically, and we see that, there's a lot of partitioning up in the highest altitudes, which we would expect. We also looked at some stuff related to the particle phase, and we're working on adding some condensation to some simple models using sort of a distribution of volatilities, and we're kind of varying that, but we haven't gotten that far, and I'll just stop.
Okay, thank you. So next up is Kelsey Bilsback.
Hi, I'm Kelsey. I'm a postdoc at Colorado State University. Recently, we've been looking at the effects of chamber experiment artifacts on OA concentrations in chemical transport models. So we basically come up with this systematic way to correct for chamber artifacts that includes fitting chamber data with the Sohm-Thomas box model, then running a pseudo-atmospheric model to fit the VBS parameters at atmospherically relevant OA concentrations, and then we update the VBS parameters in GeoSchem. And so on the right hand side of this slide, I'm showing an example of this method for alpha pinene, and we see up to a 20% change in simulated OA concentration, depending on how we're correcting for these artifacts.
Good, thank you. You have 5 seconds left, but we'll move on to Eleanor Browne.
Hi, everyone. So something that my group has been interested in recently is how the changing speciation of reactive nitrogen in the atmosphere is going to influence SOA and its properties. And so we've been aging biogenic SOA via the addition of either ammonium or ammonia. And what we see is really large changes in the effective volatility of CHO compounds in these different regimes. So on the bottom left there, you see 60% RH, and then to the right of that, 30% RH. And we see kind of different effects at these different RHs. The CHON compounds, in contrast, are much less sensitive. And these volatility changes are really large. They're on the same order that we see when you change the temperature or change the acidity of seed aerosol. And so, we have further compositional information than what I'm showing here, and we're starting to look at the different reactions that are occurring here. And I should say that this addition of reduced nitrogen dramatically alters the SOA composition, but we saw very little changes in the mass formed here.
Okay, thanks. The next one is Doug Day.
Hello, can you hear me?
Yes.
Yeah, great. Okay, this is summarizes some recent laboratory studies we've done to quantify activity coefficients relevant to SOA gas particle partitioning. Activity coefficients, known as gamma, is a metric of non-ideal molecular interactions and thus important for understanding SOA formation and evolution. So in these experiments, we rapidly oxidize gases in an environmental chamber, which form multifunctional organic compounds of a wide range of volatility that then we observe partition to a wide variety of different types of seed particles, and also track isothermal evaporation of the bulk SOA. And the upper right-hand plot shows a typical evaporation profile. And then using a model to track the gas, particle, and chamber wall interactions, we can fit an effective C-star for the bulk SOA, and thus a gamma. And then the bottom right plot shows a summary of the different systems we investigated, overall showing a gamma of around 1 when the polarity of the seed and the SOA is similar, and then increasing to around 5 when the polarity diverges in either direction.
Okay, so that's 1 minute. Thank you, Doug. Great. So next up is Delphine Farmer. Whoops, I think we went to, no.
Nope,
Okay.
that's right. I just realized we didn't have our names on there. So this is a really neat piece of work from my research scientist, Lauren Garofalo, and what we did in looking at biomass burning organic aerosol in collaboration with Joel Thornton's group and folks at NCAR and the Moonlight Project is we oxidized catechol with a couple of different oxidants, and we found this very curious behavior in which a second mode of aerosol would grow, and we would get this bimodal distribution with nitrocatechol sitting entirely in one larger mode. And what this really ended up being due to, in collaboration with Shantanu's group and Charles Hay, who's also here, is a mechanism that we think is heterogeneous condensation, in which the nitrocatechol would grow independent into an independent mode. And so more details of that will be in a manuscript that's in review. Thanks.
Thank you, Delphine. Okay, so next up is Charles Hay.
My name is Charles. I'm a PhD student working with Dr. Shantanu Jathar in Colorado State. We developed our Sum Thomas model by including many SOA governing processes as listed in the first bullet point. And we applied our model to study alpha pinene SOA in OFR. We put constraint on the processes as listed in the second bullet point, so that the only degree of freedom left is the time-dependent nucleation rate profile. We optimized the nucleation rate profile to reproduce the size distributions in the OFR at different OH exposures, as shown in the right figure. And we found that for the lower OH exposures, the profile must be delayed with respect to the first generation gas-phase product. And we hypothesized that it's either because we have uncertainty in the OH concentration estimation, or maybe their new particles are being formed from multi-generational species. Thank you.
Thank you very much. Next up is Clint Field.
Thanks, Joel. So I just wanted to share this slide. It's from a paper that we published last year. This is led by my student, Sid Pai. He undertook a considerable effort, I guess, to compare the GeoSchem models SOA simulation against 15 different airborne campaigns. So you can see them kind of squinched up in that little map. So what he was doing was actually comparing two schemes in the GeoSchem model, the simple scheme and the complex scheme. And I want to highlight the simple scheme here is really kind of a fixed yield approach that was developed in collaboration with Jeff Pierce. And the complex scheme is not that complex, but it does have mechanistic SOA formation from isoprene and a VBS for monoterpenes and aromatics. And interestingly, we saw, compared to these observations, quite similar performance against the aircraft measurements, despite really very different schemes, very different complexities. And in some cases, the simple scheme actually outperformed the complex scheme, which we were very surprised to see. This was not the result that we anticipated, and I think really leaves us scratching our head about what that means about global models, and perhaps how we think about translating constraints from the lab into models so that we can have more successful representations of SOA, and or what other limitations on SOA might be. Thanks.
All right, thanks, Clint. Next up is Jose Jimenez.
Thank you. So this slide is about a paper that we published this year about gas wall losses in Teflon chambers. So it's well known for a while that batch chambers have significant losses, but there were some more recent papers suggesting that chambers that run in a continuous mode do not suffer from these losses. And we've looked at with a model and basically showed that that is incorrect, right? So the bar plot on the right shows you the dash bars are the cases without losses, and the fill bars are the cases with losses. And you see that there are differences depending on the specific case, but they are always lower than what you would have if you didn't have walls. And in particular, there was one type of diagnostic shown in the bottom left that said, if you don't see a dependence of your yield on your seed, that means you don't have wall losses. And we showed that that is incorrect, that you can have low dependence and still have a lot of losses. Thank you.
Thanks, Jose. Okay, next up is Daniel Knopf.
Hello, thank you, Joel. Here I want to report on a paper we just very recently published in EST with my former graduate student Jinan Lee. He's now with Rainy Sung. That we developed an experiment where we can study OH and NO3 radical uptake by organic substrates down to minus 60 degrees Celsius. You see that in the upper right panel here. For example, squalene and triacontain, and we consider the amorphous phase transition, so the reactivity in squalene going from solid to liquid increases dramatically, whereas triacontain stays at much lower reactivity as it is solid the whole temperature range. So a vast data set that allows us to decouple, for example, desorption energies from surface reaction rates, because we have temperature as a third dimension. We also estimated a new Henry's law constant for OH uptake in aliphatic organics. That all should help to describe the chemical evolution of organic aerosol during long-range transport, which happens at much lower temperatures, minus 20 to minus 40 degrees typically. And we provided some simplified parameterizations of that reactivity for atmospheric chemistry models as a function of particle viscosity. That's it.
All right, thanks. Next up is Jennifer Lukes.
Hello, everyone. My name is Jennifer Lucas. I'm a professor at the University of Pennsylvania, and I am new to this community, but I very much want to connect. And so I thought what I'd do is just briefly tell you a little bit about the things that we do. So my research area involves trying to understand the transport processes, thermal and mass transport processes in nanoparticles and nanoscale droplets. And so the types of things that we can do might, and I'm trying to connect with this community to see whether they might be beneficial, but they might be able to help provide some sort of atomistic scale insight into transport processes that are ongoing in different types of aerosol, secondary organics and others. And so what we do is atomistic simulations, and we can calculate things like mass accommodation coefficients. We can look at structural evolution if we put clusters of nanoparticles into different environments. We can observe uptake, we can observe phase segregations, we can observe, we can watch movies basically vapor condensing onto different types of particles. We can observe nucleation and coalescence of different types of droplets. And so we can model things like surface tensions, viscosities, diffusion coefficients, various types of uptakes, spatial distribution of different types of species. And so we can look at morphologies and their evolution. And so I would very much love to connect with people who are doing experiments on single particles to see whether the types of modeling that I can do, which are at very small scales, might be able to connect to some of the challenges that you're looking at. So thanks for listening.
All right, thanks very much, Jennifer, and I apologize for mispronouncing your name.
Oh, that's okay. No problem.
Welcome. Glad for you to join. Okay, so next up is John Schilling.
Hi, thanks. So we ran a high-resolution AMS at the SGP site during high scale, and we've with a former postdoc of mine, we performed PMF analysis, and we were able to extract some factors that haven't been reported before at SGP. Perhaps not surprisingly, we saw that the organic aerosol that was arriving at SGP is fairly oxidized. There's some seasonal differences, but this is all consistent with the relatively remote sources of BVOCs that we think are influencing SGP.
Okay.
Thanks, Joel.
Yep, thank you. So next up is Manabu Shirali.
Hi, thanks. We are researching about viscosity of SOA and the effects on gas particle partitioning, and I want to introduce two papers. In one paper, using GECKO-A, which is an explicit detailed gas phase chemistry modeling, we implemented the method to estimate the gas transition temperature and viscosity. And here we simulated for alpha pioneer SOA. Viscosity is measured with various studies, and then we can reproduce it. But GECKO-A underestimates one order of magnitude. Maybe this is because GECKO-A is not treating out-oxidation or particle phase chemistry. And in another study, we introduced a new concept, which is mass accommodation coefficient, effective mass accommodation coefficient. And the motivation was mass accommodation coefficient is often applied without specifying how deep the molecule penetrates into the condensed space. But we developed a new equation which considers viscosity and diffusivity. And that is a very efficient method. You can use this one equation, implementing it, the Hooke-Suttigan approach. Then you don't need to apply the multi-layer model such as KM gap or mosaic, but you can simply connect to the equation to effectively consider that effect. This paper should come out in ACP soon.
Thanks, Manabu. Next up is Manish Srivastava.
Hi, so I just wanted to introduce some of the recent work we are doing, looking at biomass burning and especially modeling the GoAmazon field campaign and also the aircraft measurements. And in this case, we are using a very detailed model in WRF-Chem, looking at nucleation rates. So what you see on the left panel is biomass burning induced nucleation. So we have tried 7 different nucleation mechanisms in organic, ternary, and then ion induced and neutral. And the one which really stands out in biomass burning plumes is the ternary neutral inorganic nucleation. And a lot of this is because of the enhanced ammonia within these biomass burning plumes compared to the background of the Amazon rainforest. And as a contrast, if you see on the right, the organic mediated nucleation obviously dominates in the upper troposphere. That is due to monoterpene ELVOC formation. We also see that the plume rise transfers these nucleation events all the way up to 5-kilometer altitudes. And then if we look at the composition of particles, the SOA dominates ultrafine particle mass. But when we look at the accumulation mode particles, the primary biomass burning organic aerosol dominates, and that's at least 40% of mass. So we are working on a paper documenting our findings on this. And obviously we are tracking a lot of SOA components, a lot of biogenic SOA components, biomass burning SOA components, anthropogenic and wildfire components. And I would like to thank all my collaborators and ASR and my early career for funding. Thank you.
Okay, thanks, Manish. Next up is me. So in this study, we run detailed multi-phase chemistry model involving 30 chemical species and 4 hydrometeor types along hundreds of trajectories, output from the Mimica LES system for deep convective events, where we simulate convective events over the Southeast US and the GoAmazon campaign conditions. These are idealized runs, but we use inputs from profiles in those regions. We examine the fate of isoprene and its oxidation products, evaluating the roles of gas uptake to droplets and ice during the transport, as well as that of the chemistry induced by lightning-generated nitrogen oxides. And we find that the lightning knocks and uptake of low volatility vapors to cloud ice have substantial impacts on the types and concentrations of low volatility organics that are produced in the outflow, with implications for new particle formation and growth by isoprene in the outflow region. And so now we're simulating coupled isoprene and monoterpene chemistry in the system in collaboration with Manish and Bin Zhao at INNL. That's it. Thank you. So next up is Lindsay Yee.
Hi, this slide is showing a map of chemical diversity of organic aerosol datasets from the lab as represented in the blue bubbles and field as represented in the green bubbles. So we are currently curating about 24,000 mass spectra that was acquired using 2-dimensional gas chromatography with electron impact mass spectrometry. And it's available, it will be available under the UCB Globes Mass Spectral Library open access. We're looking at a number of overlapping compounds as indicated by the connecting lines between the data sets to better identify novel tracers and improve source attribution and chemical identification. And even though we have a ton of compounds coming from the laboratory data sets, what we're finding is, for example, if you take Go Amazon, there's still about 77% of those regularly observed compounds that do not have a definitive match in terms of the mass spectra with our other data sets. So there's still some gaps remaining between the laboratory representation of ambient OA. And with the growing database, we hope to further constrain the chemical complexity of atmospheric OA and understand how much of this needs to be represented in models. Thank you.
Thanks, Lindsay. Okay, next up is Rahul Savory.
Hi, so here we are presenting some results on the effect of particle phase state on SOA partitioning as a function of RH. So these results are from chamber experiments done at PNNL. And we're looking at growth of bimodal aerosols composed of Aitken mode and accumulation mode. And the accumulation mode is aged alpha-pinene SOA. And on top of that, we are growing isoprene SOA and looking at the growth of both the modes. And from that, we infer the diffusion coefficients in the accumulation mode. So the top plot shows how only the semi-solid aerosol model is able to explain the growth of both the modes, and which requires some diffusion limitation in the large mode. And the lower plot shows the diffusion coefficient as a function of RH. So it's only an order of magnitude increase from going from 0 to 80% RH. So there's still quite a bit of diffusion limitation even at high RH. And these results were just recently published last year in ESMT. Thank you.
Okay. Thanks, Rahul. Next up is Ala Zelenik.
Thank you, Joel. So in this work, we continue investigation of interaction between biogenic SOA particles and anthropogenic pHs, polyaromatic hydrocarbons. As we previously shown, SOA particles formed in the presence of pHs are more viscous, less volatile. They contain more oligomers. They contain unreacted pHs and products of heterogeneous chemistry between pHs and ozone. And particles formed in presence of pHs yield significantly higher number concentration and mass concentration, as shown here for beta caryophyllene. So in the most recent study, we used 4 different mass spectrometric techniques to investigate what this extra mass is made of. And we show it's coming from oxidation of biogenic VOCs. And we also examine composition of these extra oligomers and show that in some cases they could contain 1 oxidized pHs with addition of 1 or 2, 3 oxidized alpha-pinene molecules, whereas in other ones it's just significant enhanced oligomers which contain only alpha-pinene oxidation products. And if you have more questions, I will be presenting posters this afternoon. Thank you.
So, next up is Chen Chang. We can't hear you if you're speaking, Chen Chang.
Yeah, I'm sorry. Can you hear me now? Yeah, thanks, Joe. Our experimental result has shown that the optical properties of light-absorbing organic aerosols has shown higher light-absorbing abilities compared to previous reported. Our experimental measurements include the energy loss spectroscopy, which is STEM-based measurements, and also the in situ photoacoustic macroscopy. And both measurements show such higher light absorption for organic aerosols, especially in the shortwave wavelength regimes than previous reported values. So our next plan is that incorporate these optical properties of organic aerosols into the WRF-Chem models, and we want to study the photoelectric rate and the aerosol indirect effects incurred by this increased light absorbing values. And we want to discuss the different SOA formations based on our measured and observed optical properties. And our expected outcomes include some new insight into the aerosol meteorology feedback mechanisms. And the second one is the evaluation of aerosol radiative effects and SOA formations mechanism based on this observation data set restrict to the organic aerosol. And thanks.
Thank you. Okay, next up is Yue Zhao.
Okay, hello everyone. I'm Joe, a student from Professor Alex Laskin's group at Purdue University. It is my great pleasure to introduce one of the recent work about radiative effects of Browne carbon snow albedo. A lot of dissolving particles deposited on snow significantly reduce the snow albedo and therefore affect the climate through snow albedo effect feedback. However, little is known about the radiative forcing of Browne carbon snow. So in this study, seasonal snow samples were collected across the northern Xinjiang area of China. And in our lab, we employ an analytical platform with combination of high-performance liquid chromatography, photodiode area detector, and high-resolution mass spectrometry to estimate the relative contributions of different types of chromophores to the total Browne carbon light absorption. And then we calculate the extent of radiative forcing attributed to Browne carbon snow by a radiative transfer model simulation. Thank you.
Thanks, Yue. And then last but not least is Paul Zeman.
I think Paul is not online. He may have had some trouble, so I can present, since this is part of the project, I can present it for him. So what they have done here is that they studied a system of SOA formation from C8 C14-1 alkenes with OH and the high NOx. And this is a system for which the mechanism is very clear and oligomers are not formed. And then study the experimental SOA yield, which is the dashed line with the effect, and then how different vapor pressure estimation methods can simulate that growth. And you see that neither of the vapor pressure estimation methods capture the trend very well, but some do better than others. So in particular, spark and evaporation at the high carbon numbers do better, and simple systematically overestimates the yield.
Okay, thanks, Jose and Paul. And that concludes our lightning round of post presentations. Thanks to everybody who submitted one. Quite a diversity of work going on. It's really great to see all that. So.
Thanks, Joel. So we didn't have a specific Q&A for the lightning round, but I'm sure you can try and find the lightning round presenter sometime during the meeting and ask them questions, or perhaps if it relates to this specific breakout, we could incorporate some discussion around that as well. Okay, so before
Sean, sorry, we should probably mention there's a Slack channel for this breakout, right? You might have found.
Yeah, that's right. So I don't have the link ready, so maybe Joel, if you can.
Yeah, I can find it and put it in. Yeah.
In the chat, I'd appreciate that. Thank you.
Mm-hmm.
So we're now moving on to the first out of the two sub breakouts. The first one is on SOA measurements in the Southeast US. Chong-Ai Kwong is going to do a short presentation followed by instructions on how to get into your respective sub breakouts. But let me talk a little bit about the logistics of that before I hand it over to Chong-Ai. Okay, so the link to the sub breakouts is at this specific working document, and we'll share this link in the chat. Rahul, potentially, can you do that right now? Within this working document, you'll find a sub breakout number, and with that, you can navigate to that sub breakout room using the little breakout button on your Zoom application. We'll use the same groups for both sub breakouts. The first one on the AMF deployment and the second one on models to measurements to models. There will be at least one convener in each of the sub breakout rooms, and they can serve as moderator and they will serve as moderator and note taker. If additional people want to serve as moderators and note takers, do let the convener know. We'll add notes to this working document, and with about 20 minutes of discussion within these sub breakouts, we'll return back, and then the moderators will try and present a summary of the discussion within that sub breakout. Okay. Hopefully, Rahul, you've put the link in the chat window for people to access.
Yes, I just posted the link. It's a Google spreadsheet. So go in the spreadsheet and find your name, and you should be able to see which group you belong to.
Okay, great. So with that, I'll have Chong-Ai do you want to share your screen and maybe start us off on this first breakout?
I also just want to quickly say, if you don't find your name, just go to one of the breakouts.
Great. I'm JiaBin Huang, and along with our core leadership team and our site science team, we really want to thank Shantanu and the co-conveners of this breakout session for inviting us to present kind of updates on our science and siting for deployment of this third ARM mobile facility to the Southeast United States. And specifically for this group, presenting some SOA-centric considerations for both siting and measurements. So a little bit about why the Southeast US. So in 2018, DOE held a workshop where they identified the Southeast US as a priority region of interest for a mobile facility deployment because of a large amount of vegetative-driven biogenic emissions in the region, abundant locally forced shallow to deep convection, and then a strong local coupling of land surface with atmospheric processes. So we expect a 5-year deployment, right, with operations beginning in March of 2023. And I just want to note that this is a jointly funded ASR ARM project, and specifics on where we site this third ARM mobile facility, or AMF3, how we configure it and how we instrument it will be determined in part through recommendations from our site science team, right, which is composed of 3 topical areas where we're looking at aerosol, convection, land-atmosphere interactions, and then coupling and cross-cutting science between all 3 of those topical groups. Just to give you a sense of some of the aerosol science drivers that we hope to target with this AMF3 deployment, I kind of present this schematic of the processes that we want to be looking at and characterizing in the region. So the top third is kind of centered around convection, the middle third focused on aerosol, and then the bottom third focused on land-atmosphere 2A interactions. So broadly, right, our science is really looking at controls on the CCN budget within the boundary layer. So looking at new particle formation and transport. We're very much interested in biogenic and anthropogenic controls on SOA within the region. And then because of the high humidity environment in the Southeast US, we're also very much interested in aerosol hygroscopicity and the spatio-temporal variability, right? Likewise, we're very much interested in aerosol optical properties. So again, looking at the impacts of particle water uptake, biomass burning, and ground carbon on aerosol optical properties within the Southeast US. So to give you a little bit about the timeline and anticipated deliverables. So in March of this year, we gave a siting and measurement guide to ARM and our site operational partners. And from now until August, our science team and our operational partners at ARM are going to be very active with site evaluations and visits. And our first visit is going to be occurring next week, with a hope that by September of 2021, we will have a site identified, right? And then between September of 2021 and March 2023, a lot of activity relating to getting permits and approvals. And then with March of 2023, expecting the site to be operational with a 5-year deployment. So at this stage, we are still very much soliciting feedback from you in this breakout session on measurement priorities, their science drivers, and also site configurations. So just to give you a little bit of sense of what our baseline instruments and requested measurements are so far for this AMF3 deployment. On the left are kind of the planned baseline long-term continuous measurements from the aerosol observing system. So having long-term measurements of aerosol number, size distribution, water uptake and activation, chemical composition, trace gas, and then optical properties. We also have a number of requested measurements that we made so far, right? And these include the kind of ultrafine size distribution, size resolved CCN activity, VOCs and their fluxes, SO2, a quote unquote miniature AOS, so something that would be a subset of the main site AOS that we could deploy at supplemental sites and also aboard potentially tethered balloon systems and unattended aerial systems. We've also made recommendations for measurements of boundary layer temperature, water vapor, and aerosol via the Raman LiDAR and high spectral resolution LiDAR. Recommendations for aerosol fluxes via a combination of AD covariance, and in this case, CPCs, and also black carbon. And kind of strongly implied by these requested measurements are also a request for a flux tower to be part of this main site deployment. I just want to give you a little bit of sense of our siting considerations so far that are relevant to this group. So because of our desire to have both anthropogenic and biogenic, a representative sampling of both anthropogenic and biogenic impacts for siting, we're looking at maps of, in this case, maximum value maps of remotely sensed NO2 in the Southeast United States, along with locations of potential partner observational radar networks in black. So blue color being more rural, and then redder colors being more urban. And then for the biogenic influence, we're also very much interested in the spatial distribution of important biogenic VOCs. So in this case, looking at emission factor maps of, in this case, monoterpenes from the Megan model, and then also coupled with potential partner observational networks, in this case, NextRad radars, and then giving you a sense of some of the triangle site configurations we're looking at and making recommendations for. So in this case, this is just an example of potential site configurations and site locations that we're looking at. And of course, we welcome any feedback and guidance, right, that this community can provide. And so some of the persistent pre-deployment questions that our team is considering that are strongly informing our siting and that I kind of wish to pose to the community are some observational considerations. So how can we connect local, in this case, co-located measurements of BVOCs, which have short lifetime, with measurements of SOA, which have comparatively longer lifetimes, right? So there is a temporal scale mismatch. And then how can we balance tension between, in this case, flux measurements at one location, while properly upscaling to capture regional scale heterogeneity within the region? So there's an observational scale mismatch. And in terms of VOCs, as an example, how do we want to balance targeting speciation versus capturing the requisite temporal resolution and or the spatial extent within the region, given the strong heterogeneity within the Southeast US? And then because this is a 5-year deployment, there will be potential opportunities for intensive observation periods. So given the baseline set of AOS measurements that I presented, what type of chemistry intensive IOPs and associated measurements can we design as a group and as a community? So thanks.
Thanks, Shanghai. So at this point, we hope folks have had an opportunity to look at the document or the spreadsheet that assigns them to the sub breakouts. So I'd encourage people to now leave this specific breakout and go to the SOA breakout with their assigned number.
So you can see when you add a 7.5 kilometer run.
Yes, to a short summary of the discussion within the sub breakouts, and then we can move on to the next next topic area. John, do you want to start?
Sure. So just quickly highlighting what we discussed a little bit about the VOC measurement needs, and we kind of decided that speciated measurements are nice, but probably not at the cost of large breaks in the data. And there was a question perhaps for some of the people who've done more GC measurements about how much speciated measurements change in the short term. We thought it would be very important to have a high quality NOx measurement, and it would probably be good. One of the recommendations was to take a look at the expected NOx modulation using some of the already collected data to try to understand how much is expected, so you can design some of the science questions around that. Let's see. Most of the people thought that the IOP were a good idea, and that ARM has generally done a reasonably good job of kind of enabling people to join IOPs in the past. Vertical distributions of aerosol properties are nice to have if possible, and the boundary layer height measurement will be particularly important. So if there's a LiDAR that's planning to be deployed, that will be useful. I think that was most of what we talked about, so thanks.
Thanks, John. Rahul, do you want to do a summary of your session, your sub breakout?
Sure, yeah. So we had the benefit of having Chang'ai in our group. So we went through some slides again, and it's kind of similar comments or discussion on PTRMS, like VOC measurements. So PTRMS would be nice to have, but it would be done on an IOP basis. Chang'ai also mentioned something about flask sampler for VOCs. So that's a potential. It would be great to have nano SMPS and size resolved aerosol activation. For INP measurements, it would be filter based. Marcus Peters also mentioned the WIBS instrument for INP, the fluorescence based. And also filter collection for offline microscopy, particle morphology type measurements would be nice to have. NOx NOI is not a standard measurement, so again it would be done probably during IOPs. So that's my summary basically. Thanks.
Thanks, Rahul. Manish, you want to go next?
Yeah, so we talked about a bunch of things, and one of the key aspects was getting at the spatial heterogeneity of both VOC flux measurements and NOx flux measurements, because the Southeast US is a diverse region. And so we were thinking about what are the complementary instrumentations which can be included. So one idea was airborne flux measurements in IOP mode. And then the other thing which jumped out was it would be good to have complementary chemical speciation of SOA. Maybe collecting filter samples on a weekly basis or something which can be analyzed later on. Yeah, so I think the complementary measurements of fluxes, VOCs, NOx, obviously there is in the past 10 years after SOS was conducted, urban emissions have gone down, like there have been controls on them. So trying to revisit how, I mean, having these kind of measurements which can tell us what is, for example, the role of degrees of NOx, for example, on VOCs and on SOA formation in the region, and having having some of these airborne measurements, and also like trying to capture the spatial heterogeneity means having more than one site, which are so that we can look at what is the diversity of emission fluxes. That's another thing which we talked about. Thank you.
Thanks, Manish. Joel, you want to go next?
Sure. So yeah, we had some similar discussions in, we sort of centered on two or three aspects. One is the IOP aspect, and having, the key to sort of getting at Chang'ai's question about, connecting from a local site to regional scale would be to couple it with aircraft measurements. So the AAF would definitely, we'd want to train them into this process and think about how to instrument the aircraft for SOA type studies, of course. But one of those would certainly be involving VOC flux measurements and measuring oxidation products of VOCs and SOA together. And to think about the variability over the region from the aircraft, and then of course having to use models to integrate those measurements up to an understanding of how the emissions and chemistry are connecting to SOA. And then there was quite a bit of discussion on filters as well, thinking about collecting on filters to enable experiments or analyses for chemical and physical properties. So aging experiments or probing for viscosity, high resolution mass spectrometry for composition analyses, and thinking about what the frequency of sampling across the filters would be ideal to, at best thinking about nighttime versus daytime transitions, but not necessarily doing it all the time, perhaps, infrequently, but covering seasons so we can get seasonality questions answered. And then some ideas about whether or not we could be measuring bounce long-term, or if offline viscosity would be good enough for that. There were thoughts about using filter measurements to do ice nucleation. It seems that we're not sure how the continuous mode IN measurements would be run, and if it's really feasible to do that long term, but would filter measurements be a way to do the long term and then have IOP doing the continuous observations. We're not sure if hygroscopicity is routinely a measurement that's made during the AMF deployments, and if so, that's great. If not, we should try to add hygroscopicity online continuous measurements. Yeah, oh, and so then also organic carbon in precipitation. So whether you do that on an event basis or if you try to connect to other precipitation measurements going on and try to utilize that together with the AMF being where it is, to think about organic carbon wet removal or processing in the aqueous phase. That's not something most of us had experience with, but knew that it was going on in some locations or some time periods. And it could be an interesting addition to connect with the convection side of the AMF deployment. Let's see. Also, OC-EC measurements and connecting to other networks that are already in the region, both for the filter sampling possibilities, but also, should we augment sites that are, measurements that are already, sites that are already there for either filter measurements or precipitation that I mentioned, or OC-EC measurements? Thinking about how you integrate the AMF into the set of networks that are already in the Southeast US more generally. That's all what we covered.
Thanks, Joel. So maybe I'll only highlight the ones that we haven't talked so far. So in our sub-breakout, we talked about the need for good ammonia measurements, as well as robust NO2 measurements to try and understand the chemical regime under which the chemistry is happening. Another idea that was brought up were leveraging sort of low-cost sensor measurements that could be deployed in a network to capture spatial variability within that region, in addition to the ground site and in addition to the aircraft. So this would be multiple sensors in a network. Another idea was trying to capture the NOx gradient in the region, perhaps measurements of acidity, as well as measurements of low volatility oxygenated, oxidized products from biogenic chemistry to think about new particle formation and growth. And then one final point was perhaps Lagrangian sets of measurements that could be compared against model predictions. So this could be, aircraft transects. This could be fixed sites across the predominant wind direction, and so on. So I guess we'll leave it at that. We're already way past our allotted time. But let's. So I'll thank everyone for that first sub-breakout discussion, and then hand it over to Joel to lead us off on the second sub-breakout, which is on thinking about measurements, both lab and field, and their translation to mechanisms in models.
Yeah. Okay. Yeah. There's. We don't have to take too much time here. I'll mostly focus on the questions that we came up with as a group. We came up with many, like 10 or something, and I've tried to synthesize them into 3. And I'll also share those shortly in the chat so that you can have them to reference if you want. But to be honest, if you have your own things you want to discuss, related to how do we incorporate the understanding that is being gained from, say, laboratory measurements or field measurements into models, and also vice versa, how do we better leverage the insights coming from integrating our current understanding in models and comparing to observations showing where the gaps are? How do we take that insight and help design experiments in the laboratory or fields in order to sort of fill those gaps that are emerging? And of course, it's a complex set of processes involving many aspects of the Earth system. that influence SOA, and then SOA has influences from there on the Earth system in many different aspects. And so I think as part of this community, our goal is to help understand at a fundamental level these processes and properties that influence SOA, and vice versa, how these properties of SOA, its amount or its contribution to particle formation or its ability to form ice and so on, influence back on climate, so that we can represent this in Earth system models and understand better how changes in climate will influence SOA in the future or vice versa.
So Joel,
Yes.
A quick question. I think this came up in our breakout. I think you may want to give this update, meaning now with the decarbonization and reduction in emissions, air quality co-benefits, this gives a priority to this. So give it a little bit twist. And also this outstanding issue of SOA formation from fires, yes or no. So there's some areas we've made progress, some we haven't. And that would be good because this is an old plot, well, 5 years old. We need to give it a modern twist.
Yes, I mean, I agree. Not all the interactions or effects are sort of summarized in this plot. And I think for sure, fires in the future will be continuing to be important or more important than they have been in the past. And that's certainly one that there is a little flame here today. You might have missed it.
I didn't miss it. I think it's there. Just give it to the program. They like that.
Yeah, so I think any aspect of this system where SOA is, important in understanding the aerosol effects on climate writ large. So is certainly of interest here. And how we connect, though, from the measurement side to the models so that we really have an efficient transfer of knowledge up into the integrator of our knowledge, the models, right? Is I think a goal of this discussion, and think about how it's working, how it's not working, how it could work better, in terms of this community of people working on these topics. So questions for discussion then can be summarized as what you can use these as a launching pad, or like I said, if you have your own questions you want to explore in the breakout session, feel free to raise them. But what processes or properties linked to SOA formation and or its loss are relatively well documented within laboratory or field measurements that can already be better represented in models and are not being represented in models, for example. So for example, there might be processes for formation of low volatility molecules that we know the rate constants, we know the yields, or we understand the phase transitions of SOA. So we have quantified these processes in some way for a set of conditions that could be implemented in models. You can certainly feel free to raise those and discuss how they should be implemented. Also, we can think about what SOA relevant processes need better constraints from laboratory field observations, or need more model development or different model frameworks in order to incorporate or estimate their impacts on climate better. And then finally, what set of SOA relevant measurements, this sort of was discussed already in the previous breakout, but this would also be an opportunity to discuss it further in a more general way. So what set of SOA relevant measurements, chemical species, properties, time resolution, and so on, locations or different types of conditions are often missing from ASR arm deployments or experiments, but should be part of future field intensives and or laboratory experiments to improve insights from model simulations. So I'll go ahead and actually, maybe I'll just paste those questions into the chat, and you can grab them if you want to keep them. They might be useful for your discussions. With that, I think we'll just go back into our breakouts. Is it the same breakouts as last time, breakout 4?
Yep, that's correct. Go back to your original breakouts. So we'll see you here in about 20 minutes. It's 12:30 p.m. Eastern, so we'll try and assemble here by about 12:50 or so. Okay, see you guys in a bit.
I talked a little bit about, one of the things I think that's important that Colette brought up is that it's pretty clear that now models are starting to get SOA mass correct. So that's an important advancement that should be recognized and should be communicated to people. The program managers in particular. There was a little bit of talk about how modelers are, how single sites, particularly at the surface, are useful for modelers. And it wasn't, there was no definitive discussion either way, but it, you know, obviously the larger number of sites you have, the more useful it would be. And there's also something to be said for long-term measurements. So perhaps if ARM can partner with some other agencies to get some of the more long-term chemical measurements, that might be better. And I think the last thing we talked about in quite a bit was that there's probably a better need to connect between the details that can go into a box model and like a 3D model. I think that's you know, a quick highlight of what we discussed.
Thanks, John. Rahul, you want to do for the second sub-breakout?
Yeah. So we discussed mostly, you know, aerosol processing, aerosol processes, type modeling, and measurement needs. So I'll just go through some of the items like viscosity measurements, diffusion coefficients, glass transition temperature. It looks like the models are ready to accept these parameters. They are ahead of measurements at this point. So it would be great if we can improve measurements of you know, these parameters. Also temperature and RH dependence of these parameters, you know, viscosity, diffusion. There is also another way to come at this. This is from atomistic level scale simulations. So this is Jennifer Lucas's expertise. So you can predict diffusion coefficients and surface tension and things like this at that atomistic scale. And perhaps then we can use measurements to confirm these parameters better. Also, we need morphology measurements of particles, which would be useful to constrain this type of models. Measurement of chemical reactions on surfaces, or can be modeled that as well. And there is a disconnect between partitioning models and measurements at this point, and it's crucial to close that gap. And also one last thing that was mentioned was, you know, how do we specify mass accommodation coefficients? There's a discrepancy, you know, there's a lot of values being recommended, and you know, do they depend on size, different compositions and so forth. So very detailed process level discussions here. So thank you.
Thanks, Rahul. Manish, you want to go next?
Yeah, sure. So we were talking about some of the major uncertainties in understanding SOA, especially at high altitudes, under low temperature conditions and low relative humidity. So one of the things we discussed is that perhaps the evaporation, which is predicted in models right now, especially at high altitudes, is too much. And so there is a need to constrain it with measurements. We talked about some of the chemistry measurements which can be done at high altitudes. And then the other thing we talked about was what is the role of clouds in interactions between SOA precursors and particles, and how do we include that in models? For example, when you have deep convective transport, then you transport lot of the gas phase semi-volatile SOA precursors also to the upper troposphere. And how much do we know about you know, the condensation and partitioning of those precursors? We also talked about things like using larger DC simulations, but coupled to SOA, for example, SOA mechanisms to really understand how cloud convective transport at various scales, at shallow cumulus scales, at deep convective scales, interacts with SOA precursors, SOA formation, what is the role of deep convection. And then ultimately, it is important to think of we have environmental varying with altitude, temperature, relative humidity, and that has effects on the phase of particles. So how does the formation of SOA, their gas particle partitioning interacts with things like phase changes of particles, their liquid state versus solid state as they are being transported. And then ultimately, we also talked about wet removal, for example, which has been, so wet removal parameterizations in models have been shown to be over predicting things like black carbon in the upper troposphere. And then also the other thing we talked about is dry and wet convection, for example, what happens in pyrocumulus plumes. So these are some of the things. Mainly, I think the main uncertainties are now how when we are not looking at conditions like low temperatures in the upper troposphere and then the interactions with clouds and convection. This is something we should think about. And then one final thing, like in terms of looking at the molecular diversity of compounds from SOA. So AMS gives us some information, but obviously the molecular diversity is much more than that of particles. So thinking about that diversity and what that means for modeling is another thing we discussed. Thank you.
Thanks, Manish. Joel, you want to go next?
Sure, yeah. We had similar discussions to the past few. Definitely a common theme here is low temperature chemistry and properties. Getting better measurements thereof would be very useful for constraining some of the processes in models that are influencing organic aerosol throughout the entire troposphere. Some properties that we thought could be measured more often or more routinely would be particle bounds. Even though it's semi-quantitative, if you measured it in an online kind of continuous way, it'd be really helpful for testing parameterizations of phase state, especially not just in the field at a ground site, but also at different conditions. So if you could somehow precondition the aerosol before it's coming into the bounce measurement, say for a different temperature, that would be very useful to include in chamber measurements and or field measurements. This issue of phase separation, it's not clear how to measure it, but best, but it's clearly going to influence how we properly simulate SOA. And there's not enough measurements thereof to understand how it evolves in time and space. There are ways being employed already, maybe more could be done in this way to utilize chamber measurements that already exist and to improve the way that chamber measurements are translated into models. So the example was Kelsey's poster today, where essentially employing better wall loss estimates and better distribution of organic aerosol masses to better simulate how you would translate these yields in chambers to to atmospheric properties is something that we could be more careful about doing as a whole in the modeling community. Something that's not in models, not in many models that could be put into models is auto oxidation process. It's a bit, we discussed how it's a bit counterintuitive. It's probably easier to put into larger scale models in a simplified way than it is to put in an explicit model like ECHO, but that it's something we know a fair amount about that could be better implemented in Earth system models. And finally, if we're doing an Earth system model, having longer term OA mass concentration measurements outside of the US, so really a global scale view of the needs here, and how we go about making that happen through this program is maybe not so clear, but it's something that we would want to encourage reaching out and making connections to other regions to engage and get more SOA measurements or OA measurements in general throughout the world. Yeah, that's the extent of our discussions.
Thanks, Joel. Some of the same discussions happened in our sub breakout. So it's nice to know that there's sort of similarity in thinking around this issue, but there were a few differences, and I'll point those out. One was, what do we do with the measurements, the complexity in measurements, particularly in the lab and the field, and how we compare them against model predictions. One example given was Lindsay Yee's slide today. There's thousands and thousands of these species measured, how do we appropriately compare them to model predictions that cannot realistically track those many species, right? And so how do we condense the measurements to evaluate models? One thing that was brought up was the similar amount of data that's been collected on fires as part of some historical field campaigns. Another thought was when we parameterize, when we develop SOA parameters from chamber experiments or lab experiments, we do that with, traditionally do that with single compound systems, but there's non-linearity to consider in the chemistry that affects SOA mass, yield, as well as its properties, right? So we need to do more laboratory experiments on complex VOC mixtures. How does a diversity of monoterpene emissions affect SOA mass yield, as opposed to looking at them as a linear sum of the constituents. So cyclic versus acyclic, how would perhaps drought affect biogenic VOC emissions, and what would their influence on SOA be? We did talk about temperature, but I'll skip that. And then we had a short conversation on what are the important SOA dimensions to capture in models. So mass is one, but what else do we would want models to capture? So perhaps the size, aerosol size distribution, hygroscopicity, mixing state other than simply sort of a binary internally versus externally mixed state, volatility, viscosity in some form, either the diffusion coefficient or ability to bounce. I guess I'll stop there because we're already 5 minutes past our breakout session. So I'd like to thank the conveners for putting this together. I'd also like to thank all the participants. I think you all learned something new today. We can continue this discussion on the Slack channel. Maybe we can share another link to that for not only the duration of this conference or this meeting, but sort of beyond it. And with that, I'll let you guys go and get some lunch.
Thanks, John.